All right, so what's the idea behind, so let's look at the informal idea behind a confidence interval. And I'm going to draw a sketch of this, but then I'm actually going to bring up the page. I'm going to bring up the, I'll draw a sketch of this, but then I'm going to bring up the, animation that I have on WAMAP that does this a little bit better. Let me go ahead and clear this. I think I just saved it. I'll clear it again. Okay, and we'll generally use the abbreviation CI for confidence intervals. Okay, so let's draw the real population. So I'm going to make a sketch here of the real population. All right, so this is the real population. Real population is distributed this way. A bell curve. Okay, the real population looks like this. Okay, and if I wanted to, I could highlight the boundary values for the middle 95% of these values. So there's some range here where I've actually, so what's in the tail are the extreme 2.5% on each side. So what I'm looking at here, this range here is the middlemost 95% of my population. Right? Now, if I look at this, if I draw this, I know that there's some actual average. All right. In this case, I'm referring to a population proportion just to make our lives easy. So there is, so this is this position here is at P, this is P star. Okay. And I know that 95% of the time I will find sample proportions that fall in this interval. Okay, 95% of the time, as I'm drawing random samples, 95% of the samples will have proportions that fall in this range. Okay, so what I'm going to do is I'm going to temporarily go and grab a proportion. So I grab a sample, and its proportion falls right here. Okay, so what I'm going to do is I'm going to take this interval length here, and I'm going to say, well, if I add that length to both sides of my proportion, my sample estimate may not have been P star, but this new interval captures P star. I might have a P hat over here. And again, if I add the interval estimate to it, I get that value. I might have a P star, P hat that's very close. Okay, I'm adding that length to it. Okay. Okay, and again, we kind of expect values, but every once in a while, we're going to end up with a value that looks like this. I'll switch colors just to emphasize the point. Every once in a while, we're going to end up with a value like this, a sample, because it is possible to get these large extreme samples. And now when I add my confidence, when I add that sort of margin of error that I was using, now I've actually missed this interval, unlike the green ones, failed to actually capture this value. Okay, so here's the first end of class question for you. And this is a text question. So this one's more writing out in text. Okay, so as I've drawn here, if I kept drawing these intervals, drawing samples, calculating p hat, and adding this error term, how many of my intervals, what percentage of my intervals will fail to capture the actual population proportion of P star? Okay, so that's the question. That's the first end of class question for today. And what I'm going to do now is I'm going to go ahead and bring up the while you're taking a moment to either copy that down or even answer that, I'm going to go ahead and bring up WAMAP.
Are you looking for like an interval notation, or interval estimates, or just?
I'm just looking for what percentage. So okay. What percentage of these intervals would miss?
Okay, thank you.
Yep. All right, let me go to WAMAP.
Can I ask a question?
Of course.
Are we supposed to be using like the percentage of the little p-values that you wrote down?
Nope. Think of this going on infinitely many times.
Oh, okay.
So if I had every possible sample that could have ever been drawn, what proportion of them would miss? Okay. All right, so this is the graphic. I'm going to go ahead and switch the share to my screen. Can everyone see the WAMAP graphic?
Yeah.
Okay, so here's the idea. We don't know what the population mean is. So I draw a sample, okay? And when I draw that sample, I'm going to calculate the confidence interval. Okay, so there's some process by which to calculate that interval. All right, so again, we don't know the mean. So we draw a sample, and then we calculate a confidence interval with that sample. If I did that a bunch of times, okay, if I did that again and again, I'd have a lot of different intervals. Some of those would capture the true population proportion. That was that dashed line down the center. Some of them will capture. In fact, if I'm doing a good confidence interval, most of them will capture. But every once in a while, we'll find one like this one here that shows up in red. We'll find one that does not actually capture the interval. That's the idea behind confidence intervals. This graphic here is probably a little better than what I just did in the whiteboard, but I apologize that I'm not that good at drawing stuff like this. All right, questions for me at this stage? All right, let's give the formal definition then. So I'm going to go ahead and clear the screen here. So let's give the formal definition of a confidence interval. Okay, so the idea of a confidence interval, it's something that goes like this. Using a procedure or protocol like this one, okay, whatever the protocol that we're using is, using a procedure or protocol like this, 5% of the intervals. Oh, sorry. I need to give a confidence. Sorry, so I forgot to give the confidence. So using a procedure protocol like this, so I need to give the confidence level first. So let's do that. So our confidence. Let's say we want to do something with 98% confidence. Okay, so this is what we call our confidence level. So we want to be 98% confident. Trying to move this and not having much luck. Okay, so if we want 98% confidence using a procedure like this, then what we end up with is 2% of the intervals are wrong, i.e. they miss the value, but but 98% of the intervals must be right. Now, what do we mean by right? Well, the process or whatever procedure or protocol we're using is right if we have okay, so again, what we mean by right is the following. Right means that the interval actually contains the population proportion. All right, so let's do this process. Now, if you'd like to follow along, I'm actually going to just walk you through. I'll walk you through this using. So let me demonstrate. So this is the definition of a confidence interval. It's a procedure or protocol that achieves the correct result, the given confidence level, whatever that confidence level is. That's the percentage of the time the procedure actually gives you the correct result. All right. So let's take a look at this process. All right, so I'm going to go ahead and clear this. And if you want to follow along here, if you want to follow along with what I'm looking at, if you go onto back onto WAMAP, I believe I put a copy of this so you can do it. So I have the Excel template. I'm actually just going to walk right through this Excel template. If you click on the dark green folder in the current module, you can follow along with what I'm doing here. Okay. I'm going to go ahead and bring a copy of it myself. I've got a copy here saved. I'm going to bring this up. Lecture, documents, 13. All right, so I have a copy, and I'll type on this copy, but let's actually go through this together. So I really wish it would let me share. I wish it would let me share. Am I sharing? I'm sorry, what is sharing? The whiteboard?
Yeah, the whiteboard.
Okay, where's my whiteboard? All right, I'm gonna have to stop it because it's not showing me the whiteboard. All right, stop share. Show me the whiteboard. There it is. Okay. All right, so step one. So you always start by finding the point estimate, okay? So we always start by finding the point estimate. So here's the scenario that we're looking at. Okay, so here's our scenario. A poll of 975 adults found that 507, I believe climate change is a real man-made threat. Okay. All right, so this is the scenario that we're currently working with. A poll of n equals 975 adults found that 507 that believe climate change is a real man-made threat. So our question then becomes, so the question that's driving what we're doing here then is, what can I say about the population? In other words, what proportion of the population actually believes that climate change is a man-made threat? Okay, so step one is to find the point estimate. All right, so the point estimate is, I'll go ahead and write this out here. Whoa, what happened? All right, so our point estimate is p hat is k over n, which in this case is 507 over 975. Which is about 52%. I'm not sure. Maybe it's exactly 52%. I don't think so, but no, it is exactly 52%. Look at that. All right. But the point is, this is a point estimate. This is just a point estimate. It is probably too narrow, too restricted to give me a clear sense of what the actual values are. So let me go to the PowerPoint. Sorry, not the PowerPoint. Let me go to the so this is the handout. So this essentially is an Excel sheet, but it's a template that you can use to actually do these calculations. So the very first thing that I'm going to do is I'm going to actually calculate the point estimate. Okay, so in cell B1, I put the value K, which is the number of successes. In cell B2, I put the value N, the total sample size, 975. P hat, this is the formula that is entered right here. This is just these divided, which gives me 0.52. And because I know I need it for my calculations, I'm going to calculate also 1 minus P hat, which is essentially the proportion of in this case, it would be the proportion of people that don't believe climate change is a man-made threat. Okay, now there's sort of a step, there's also a step 1.5 I'm going to put in this mix. It's not spelled out in here. So let me go ahead and save this, and I'm going to go ahead and get rid of this part. Get rid of this. I knew that was going to happen. All right, give me a moment so I can redraw this so it actually doesn't disappear next time. All right. All right, so step 1.5, if we want to call it that, is to describe the sampling distribution. So step 1.5 is to describe the sampling distribution. Okay, and so in this case, what we're asking is, we're essentially saying, hey, is our sampling distribution normal, or more importantly, are the p hat normally distributed? And if so, what would the mean and standard deviation be for that distribution? So what I can do here is I can calculate the count variance. So I know that if the count variance is 10 or larger, remember that's n times p times 1 minus p. Now I don't know p, so I have to use p hat in this case. So n times p hat times 1 minus p hat. If I punch this in, I get the value of 243 and change, which is greater than or equal to 10. Okay, so this suggests to me that yes, it's actually a normal approximation is reasonable. So the normal approximation is reasonable. So if I were to switch over and look at this on my handout, so what I did is I just calculated the variance here. Okay, so this is the variance, the count variance. And we see that variance. And we see that it is indeed greater than 10, so we're all good. So that's the count variance. That's what we actually have here. Okay, again, that's what we were calling step 1.5. All right, now what we need to do is we need to calculate the standard error. So, well, sorry, let me finish this off. So what we need now is if we go back to the PowerPoint slide, the whiteboard, we come back here, now we know that we can actually describe our distribution. More specifically, we know for our distribution, the average of our sample proportions would be p star. Now again, we're looking for p star, but we're going to plug in p hat for that. And we know that the standard deviation or standard error of those sample values would be p star times 1 minus p star all over n. And this again would be a normal distribution. The only problem is, and it's kind of a big problem, is that these are all unknown. I don't know what these are. These are unknown. Okay. So what I'm going to do is, instead of using these values, I'm going to use estimates for all of these values. Instead of using these values, I'm going to use estimates. Right? So that's the process here. So what the estimates for all of these, let me go ahead and clear part of this screen off. Okay, so step two is to calculate the standard error, but to do that I need these estimates. So what I'm going to do is I'm going to do the following. Okay, so we have, I need this value here, but I have to estimate it. So since I have to estimate it, I need an estimate for this value. I'll put a hat on it just as a reminder that it's an estimate. So what's the best estimate I have? Well, it would actually be my current sample proportion. So I also need an estimate for my standard error. Okay, again, it is just an estimate. So the best thing that I have for that would be to use the formula here, where I'm just going to plug in my p hat.
Wait, didn't you just say that you don't have any of those numbers?
I don't have P star. I don't have the population, but I do have an estimate from my sample. That's the subtle difference between these two.
Okay.
Okay. So again, key point is that these are estimates. I'll reiterate this. So the key is that both of these are estimates, which is why we're sort of adding that extra hat onto that to reiterate the fact that it is indeed an estimate.
Would the p hat be referring to k over n, so 507 over 975, which is 52%?
That is exactly correct.
Okay.
Yep, that is exactly correct. Okay. All right, so again, these are the estimates for these values here. Okay. So what I'm going to do is I'm going to go ahead and erase this because I want to say what this is. So the step that we just did was step 2. Step 2 is to calculate the standard error. All right. And this is the standard. So the standard error is this value right here. All right. So let me go back to the other screen because that's what we have here. All right. So we have, again, we know that the mean is 0.52. So all I've done here is to calculate the standard error. Let me make this a green, preferably a dark green. So this is the standard error. Now, technically what I did in this process, I broke it into 2 pieces. I actually broke this into 2 parts where I first calculated, so I calculated what's under the square root and then I took the square root of it. But this is, so what's listed here is the standard deviation. This really is the standard error. Okay, it's the standard deviation of the sampling distribution, which is the standard error. So I'll sort of just reiterate that. Okay, the standard deviation for the sampling distribution equals the standard error. All right, so that value is 0.016. All right. If I come back to the whiteboard, I can plug that number in. So this value we just calculated, so this value is 0.016. Okay. Now, the next step is to get the critical value. So the next step is to get the critical value. We want to get the critical value. Okay, so we want to calculate the critical value, and how do we do that? Well, let me go ahead and erase this part up here. Okay, so the idea of the critical value requires a confidence level. All right, so that's first step. So I'll go ahead and make note of that. Okay, so let's say for our purposes, we want a confidence level of 95%. Okay, so the critical value requires a confidence level, and we have to pick what that is. Let's go ahead and say 95%. Now, with this information, then what we do is we sort of say, well, hey, if I were just to draw a general curve, so if I were just to go ahead and draw a general bell curve, okay, standard normal bell curve, okay, I want to know where are the boundary values that separate the So I want inside here, I want 95% to fall. I want the middlemost 95% of values. So if there are 95% values in the middle, then I know that there's 2.5% in the tails. So out here, there's 2.5%. Okay, so what I'm looking for, again, we use the notation, these critical values would be indicated as minus Z sub CV and plus Z sub CV. Okay. Now I can get this value directly just using the norm S in function. So if I did norm S in of 2.5%, that lowest most tail, 2.5%, this will actually give me the critical value that I'm looking for here, which is negative 1.95996, et cetera, but I'm just going to round it to negative, 95996 and change. So what I do is I recognize that gives me this lower boundary. It's the same value up here. So my critical value would be plus or minus, I'll just round to 2 decimal places, 1.96. Now, just as a sort of a reminder, this value here, what is this? This is really just 1 minus 95% divided by 2. Now, in Excel, so I've already given the Excel code here, but let's actually take a look at what this would actually be in the handout that I have. Okay, so here's the handout. So here we've calculated the critical value right here. This is the critical value. Let's make that be red. Okay, so that's step 3, is to calculate the critical value. Now from here, we calculate the margin of error. So the last step is to calculate the margin of error. The margin of error is our wiggle room. The margin of error is the amount that we're going to add to our interval. So step 4 is to calculate the margin of error. So what we're going to do is we're going to take the interval that we have, we're going to use this critical value to help us calculate that error term. All right, let me go ahead and erase this part. So using that critical value, the margin of error is margin of error equals the critical value, Z sub CV, or what we call our multiplier, times our estimate for the standard error, which again is the standard deviation of the sampling distribution. So this is 1.96 times 0.016, and if we punch this in, we should get a value of, so if we go back to Excel, this should give us a value of about 0.0, sorry, actually, I do think I do want to write that. So this is about 1.96. This value was 0.016. We multiply those, and that gives us the value that we're looking for, which is about 0.031359 and change. Again, we want to keep as many decimal places as we can. We want to keep as many decimal places, which is the advantage of doing it in Excel, because we can just reference back to the cell that we're talking about. So this value here is the margin of error. Step 4 is to calculate the margin of error. And this should be purple. Okay, so we're taking the critical value, which we have here, and we're multiplying it by the standard deviation, which are the sampling standard deviation we have up here. I'm going to try highlighting these, fingers crossed. So this is, go away. This is, I'll put that in pink. Okay, that's the red value. And this is the green value. We multiply those, and that gives us the desired margin of error, which we have here. And purple. Okay. All right, last but not least, we are almost done. The final step now is to calculate the actual confidence interval. So let me go back to the whiteboard. So step 5, we're almost done. Let me clear this out. So save this, get rid of this. Okay. Okay, step 5 is to calculate the confidence interval. All right, so what is the CI? The CI is as follows. Okay, so the confidence interval is simply the point estimate we started with, that was p hat, and now we are going to add and subtract the margin of error. That's the wiggle room we just calculated. So writing it out as an interval, this would be, so the interval, and it kind of doesn't matter if we use brackets or square brackets, so just be careful what Walmart might be asking for if you're punching in answers. So we take the value minus the margin of error, and then we go up to the value where we take the point estimate plus the margin of error. And that gives us our interval estimate. So in this case, the values would be, so taking the values that we have from the Excel sheet, it would be 0.52 plus or minus the value 0.031 and change. And if I add these values up, we should get the interval 0.489 up to 0.551. Or in other words, we could say that it's about 48.9% is less than the population proportion, which is less than 55.1%. And I'm 95% confident that the population proportion is indeed somewhere in this interval. So again, let me just reiterate this point on the, handout. So all we've done here, so this, all this is taking the orange value from up here, that mean of 0.52, that's what's in cell B8, and then we add and subtract the margin of error, and this gives us the, so this is step number 5. This gives us the boundary values for the confidence interval. And that is the, okay, so now that once you have this, you essentially have a template that you can use to calculate every value, to calculate all of the results. Okay. So again, to clarify, the last step is, now what we want to do is we essentially, there is a step 6, and that is to summarize our findings. So step 6 is to summarize the findings. We want to summarize the findings here. So again, using this interval, I'll retain the interval here. I'll erase everything but that interval. Okay, so how do we actually summarize the findings? Well, I would say something along the lines of so I'm 95% confident that the true population proportion is between 48.9% and 55.1%. So that's essentially my claim. So the question then would be, so what if someone said, well, wait a minute, what about this? Can you say that, so what if someone wanted to say, well, more than 50% of the adult population believe climate change is a man-made threat? Well, so this is where it's tricky. This is where it gets a little tricky, because does this interval agree with this statement? And the answer is yes. 50% is in this interval. Okay, so it agrees with it in the sense that it doesn't contradict it. But the problem is, it does not. So this interval or this value that I obtained here does not prove this statement. It doesn't prove it, because values less than 50% also agree within this interval. For an example, it could be the case that the proportion is actually 49%. Maybe 49% of the population believe climate change is a man-made threat, in which case I still could have obtained my sample with 52.0%. But yeah, so this is the question where we're sort of forced to ask our question, well, what's the difference between an interval that agrees with what we have? So the interval agrees with it, but it doesn't prove it. So values less than 50% also fall in this interval, and that's really important. Okay, I'm going to go ahead and clear the screen here. Okay, so again, saying it this way, does this interval agree with what we're saying? So let me make this larger. So 48% to 55.1%. Yes, this interval does agree. So it at least agrees in the sense that it doesn't actually contradict what we're trying to claim. But if we're asking the more poignant question, does it prove what we want? So we're asking, does it prove that 50% or more is the actual result? The answer here is no. It does not prove it. Okay, no, it doesn't prove it. And that's because values less than 50% also agree with this interval. Meaning P star could actually be something like, which is indeed less than 50%. Now, this isn't to suggest that it can't work. This isn't to suggest that it can't give us the result that we want. Okay, so let's look at this idea of argument versus proof, and let me give a scenario where it's clearly the case. Okay, all right, so let's do the following. I'm going to go ahead and clear this. So we're thinking about this idea of agreement versus proof for a little bit here. So it's one thing to have a confidence interval agree with your claim, but that's not the same thing as proving it. Now, what I do know, and this actually is pretty much a confirmed result. So we know that 98% of climate scientists believe that climate change is a man-made threat. So it's a threat to the world. Okay. So so we know that 98%. So if we took a sample, we'd get about 98% of the climate scientists we poll would say that change is a man-made threat. So the question then is this. Okay, so if this is my claim, what do you guys think? What can we conclude if this is the claim? Does the interval we found agree with this statement? Agree with this claim? Yeah, it was 48. If we take any value in this interval, all of those values are very clearly less than 98%, yes? And if we think this is the interval that's close, even if we had bigger confidence, the interval would get a little bit bigger, but is it going to get all the way up to 98%? Probably not. Now, the next question is, well, does it prove it? Does this prove what we're looking for? And here's where I'd say, yeah, this percentage is so clearly out of the bounds of what this reasonable estimate is. Even if we expand it a little bit, I would go as far as to say that yes, this actually does prove. This does prove the claim that we're being made. Well, maybe, because rare things still happen, but I think it's so. This is where statistics gets interesting. We start moving to this idea of proof versus we start moving this idea of proof to agreement to justification, and this is the nature of statistics. All right, I just realized I kind of missed a point along the way where I wanted to give the next end of class question, but this is as good as a place to do it as well. So let me give the next end of class question, which is referring back to this interval here. So I've got to get rid of this. So here's the next end of class question. Let me make this a little smaller so it fits on here easily. So here's the end of class question number 2 is, would the 90% CI for this sample be bigger or smaller? And then briefly explain why.